Okay, so I'm gonna go over how to properly propagate uncertainties when you have an equation defined by variables that have uncertainties of their own. So when you look at like a rectangle, there could be uncertainty in the length and uncertainty in the width. So you can't just multiply the uncertainty in the length times the uncertainty in the width to get the uncertainty of the area. There's actually a standard procedure how you do it to make sure that you get the uncertainty properly. So there's some mathematical equations that you need to know to figure that out. And I know that this might be kind of fast and confusing for some of you, so please ask me how I got to some things because I'm kind of going over things quickly. So I'd be more than happy to explain how I got something. But I'm going to want to make this video brief. So we have a length and a width, and you're going to be able to obtain an uncertainty in the length and an uncertainty in the width. That's going to come from like how accurate of a ruler you have, or some kind of other measuring device that you have. The main thing with uncertainty is you want to just be able to justify why you had that number as an uncertainty, and usually it's like because a ruler is only so precise. So the formula is the uncertainty in the area squared is the uncertainty in the length squared times the partial derivative of the formula for area squared. So a partial derivative just means that you treat w as a constant and you differentiate with respect to length. So this is pretty much just d/dl of length times width, and width is just a constant. So you will be able to take w out of the derivative because it's just a constant in this case. Now that's added to the uncertainty in the width times the partial derivative with respect to the width times your formula for the area. So now we treat length as a constant and we differentiate with respect to w. So when you plug all that in, you get that the uncertainty in the area squared is the uncertainty in the length squared times the width squared. Because if we take the derivative of this, it's just w because the L, it's just like differentiating x, but you're differentiating L this time. So so this ends up just being w, and then you got to square it. And then the same thing for when you have the uncertainty in the width, you differentiate this with just respect to w, and then you just left with L, and then you have to square that. So that's the general formula. Basically how it works is you have to differentiate each of these variables using the partial derivative for each specific one for every variable that has uncertainty. So if it was like a cube, there'd be uncertainty in length, width, and height. So you'd have 3 terms, and you need to differentiate with respect to length, width, and height. So then you just have 3 terms, all with like sigma L, sigma width, sigma height. Sigma, this is just the Greek letter sigma. When it's uppercase, it's actually weird. It looks like this. So I don't know why it's different, but that just means the uncertainty in a certain quantity. In your guide, it says delta, so in this case I'm substituting sigma for delta because that's how I learned it. So when you want to propagate uncertainty for your lab report, you have something where you have acceleration as g times the sine of theta. So you're going to have to find the uncertainty in the sine of theta. Well, if you measure the height and you measure the length, the sine of theta is the opposite divided by the hypotenuse. So the sine of theta equals that, hypotenuse over length. And then you can actually just find the uncertainty in the sine of theta. You don't have to find the uncertainty in theta, actually, which is something that I should have told you during lab. But I told you to find the uncertainty in theta, which actually complicates things more. So just find the uncertainty in the sine of theta, and that actually makes it a lot easier. So that, oh, and by the way, you have to find the true uncertainty in this, you have to take the square root of the whole thing. So if you look at like your lab manual, and it gives you the uncertainty for a product rule, I think it's just this, but they didn't go into like derivation. So here, if we take the derivative with respect to just h, we're left with just 1 over L, because L is a constant, so we're just basically taking the derivative of h and then multiplying it by 1 over L, so the derivative of h is just 1 when you're differentiating with respect to h. But in this case, we're actually differentiating with respect to L. So this is like taking the derivative of 1 over L. And then how you do that, this is like dl of L to the minus 1. So you bring the negative 1 over, you have negative L, and then you increase this by 1 L to the negative 2. So that's just negative 1 over L squared. But in this case, we had h, in which h is a constant, so we have to multiply by h, so that's why we get that. Now you may be wondering, well, how do we get a negative derivative? How does that make sense? How can we have less uncertainty? Because then wouldn't that just subtract it? Well, actually, that's why the squared comes in. So once you square it, it cancels out the negative, so that's why there's the squared in this formula. So some of you may not have found the uncertainty in the height and the uncertainty in length, but with your lab reports going forward, it's very important to find the uncertainty in everything so you can do this propagation. Be on the lookout for our videos on how I want you guys to use Excel, and then how I want you to find the uncertainty of things that don't come from like a prediction equation.